Dear learners, I greet you all. My name is Odoi Henry, a teacher of physics at Namugongo Secondary and Vocational School. Our lessons are uploaded on our YouTube channel. We request you to open and read them, and in case of any challenge, you can call us for consultation. Today, I'm going to teach A-level physics. Our dear students of physics A-level, you all know that physics A-level physics has 3 papers. We have paper 1, paper 2, and then paper 3. The paper that I'm going to discuss today is paper 1. And the topic of our discussion today is gravitation. Gravitation falls under mechanics. By the end of this lesson, I expect you to be knowing the following. Number 1, you should be able to state Kepler's laws of gravitation and then Newton's laws of gravitation. Number 2, you should be able to derive the dimensions of the universal gravitational constant G and then state its unit. Then number 3, you should also be able to use the Newton's laws of gravitation to verify Kepler's third law of gravitation. And then number 4, you should be able to derive an estimated value for the mass of the sun. Gravitation comes from the word gravity, which means force, and it is the force that pulls object towards the center of the earth. We can therefore say that it is the force of attraction between two bodies in the universe. An example, a force which pulls down the ball that has been kicked up in air. Also, when a leaf drops from the branch of a tree, it does not go up. It is being pulled down due to force of gravity. We can also consider force of attraction between the earth and the sun. We can also consider force of attraction between the earth and the moon. Gravitation as a topic deals with the motion of planets in the Earth's gravitational field. We know of very many planets in the universe. Like we have the planet Earth, we have the Jupiter, the Mars, Uranus, Neptune, Pluto, and so on and so on. Today we are going to put our major focus on the planet Earth. Now, this motion of planets is governed by 2 laws. That is Kepler's laws of gravitation, and then we also have Newton's laws of gravitation. We are going to state each of these laws separately. Kepler's laws is divided into law 1, we also have law 2, and then we have law 3. Kepler's law 1 of gravitation states that the planets revolve around the earth in elliptical orbit as a point of focus. Then law 2 states that the imaginary line joining the planet and the sun sweeps out equal area at equal time interval. And then lastly, law 3 states that the square of the period of revolution of the planet about the sun is directly proportional to the cube of the distance between the earth, between the planet and the sun. i.e., if the period of revolution is t, and then the separation between the planet and the sun is r, then we shall say that the square of the period of revolution of the planet around the sun is directly proportional to the cube of the distance between the planet and the sun. Now we have looked at law 1, law 2, and law 3. They are all talking about planet moving around the sun. Therefore, it can also be called Kepler's laws. These laws here can also be called Kepler's laws of planetary motion because it involves motion of planets. Then we also have Newton's laws of gravitation. To state this one, we shall consider two bodies in the universe. We shall have this body 1 with the mass m1. Then we shall also have this body 2 with the mass m2. Let us say that the separation between them is r, like that. Then of course we shall also have the force of attraction between those two bodies, F. Newton's laws of gravitation states that the force of attraction between two bodies in the universe is directly proportional to the product of the masses of the two bodies and inversely proportional to the square of their mean distance apart, i.e., shall have F being directly proportional to m1, m2, we can call this one equation 1. Then also have F being inversely proportional to 1 out of r squared. We can call this one equation 2. When we combine equation 1 and equation 2, we shall come up with F being proportional to m1, m2 all over r squared. And when we remove the proportionality sign, we introduce in a constant g, then m1, m2 all over r squared, where g is a constant of proportionality in this case, and we call it the universal gravitational constant. This expression that I've written here is from Newton's laws of gravitation, which states that the force of attraction between the two bodies in the universe is directly proportional to the product of the masses of the two bodies and inversely proportional to the square of the mean distance between the two bodies. Dear learners, we are also going to look at how to derive the dimensions of the universal gravitational constant G and how to state its units, the SI units. The SI units. So, we shall have to look at this one, dimensions of G and its units. Few days ago, we looked at dimension of physical quantity when we were just introducing mechanics. And we said that dimension of physical quantity is the way in which a given physical quantity is related to the fundamental quantities of length, mass, and time. Dimension of a physical quantity is denoted by that symbol. Therefore, if we want to write dimension of length, we write like that. Dimension of mass, we write like that. Dimension of time, also, we write like that. Dimension of length is capital L. Dimension of mass is capital M. And dimension of time is capital T. To derive the dimension of G, we shall go to Newton's laws of gravitation. This equation which we had this, that F equals to G M1 M2 all over R squared. We just make G the subject and it will give us G equals to F R squared all over M1 M2. And if we want to get dimension of G, we shall write like this. Dimension of G will therefore be equals to dimension of force times dimension of R squared divided by dimension of M1 dimension of M2. Dimension of mass, M1 is mass, so dimension of mass is just capital M, so we shall put here capital M. Even M2 we shall put there capital M. R squared, we have seen that R is the distance between the planet and the sun. So R is the same as length. So R squared will be the same as L squared. Then F is the force. So we shall need to derive the dimension of force. Dimension of force from Newton's second law of motion, we have F equals to ma. This is mass, this is acceleration. It therefore means that if we want to get dimension of force, we shall need dimension of mass times dimension of acceleration. Dimension of mass is capital M, that one we know it. But dimension of acceleration, we don't know it. We know very well that acceleration is defined as the rate of change of velocity with the time. So it is V out of T, meaning that dimension of acceleration will be dimension of velocity divided by dimension of time. And also velocity is displacement over time. The rate of change of displacement with the time. So dimension of velocity will be the same as dimension of displacement divided by dimension of time. Displacement is the same as the distance, which is length. So dimension of velocity will be capital L all over dimension of time, which is capital T. This one gives us L T power negative 1. And we can substitute it here now. Dimension of acceleration now will be L T power negative 1 all over T, which will now be L T power negative 2. After knowing that, we can therefore substitute up and we get dimension of force equals to dimension of mass, which is capital M, dimension of acceleration LT power negative 2. For us to get dimension of G, therefore, we just substitute now these values here. We shall say dimension of G will be equals to dimension of force, which is M L T power negative 2. Dimension of R squared is L squared divided by M squared. So dimension of G will be equals to M, capital M, negative 1, L cubed T power negative 2. This expression that I've just written is the dimension of the universal gravitational constant G that we have been deriving. After getting this, we can also state now the units of G. And the units of G we can get 1 from this equation and then 2 from this very one here. Let us look at this one. This is G equals to F R squared. This is force, this is distance, then masses. So we shall have, this is Newton, SI unit of distance or length is meters, so it will be meter squared divided by kilogram squared. Therefore, 1 unit of G will be Newton meters squared per kilogram squared. This one is squared per kilogram squared. That is 1 unit. And then the second unit we can get it from here. This is per kilogram. This is per meters cubed, because it is length, per kilogram, per meters cubed, per second square. This is time. So the second unit is per kilogram, per meters cubed, per second square. Dear learners, this number 1 and number 2 are the units of G. You can use any. You can use either this one or you can use this one here. Now, we have looked at Kepler's laws of gravitation, which we say that can also be called Kepler's laws of planetary motion. We have stated law 1, law 2, and law 3. Tomorrow when they ask you to state Kepler's laws of planetary motion, you don't just state law 1 and you keep quiet. You have to state law 1, you state law 2, you state law 3. And then they can also ask you to state Kepler's laws, Newton's laws of gravitation. After stating Newton's laws of gravitation, they can ask you to derive the dimensions of G, which is the universal gravitational constant, and then stating its units. We should be able to know all those. We are going to end here briefly, and we go for a short break, then we shall come back. Thank you very much.